Okay, okay. So thank you. First of all, I thank the organizer of this particular conference to have invited me for this particular talk. Uh, my name is Dr.Suraj B Vishwakarma. I'm assistant professor at Vidyavardhini College of Engineering and Technology, Vasai Palghar. The title of my talk is Annealing Effect on 100 kV Silicon Negative Ion Implanted SiO2 Thin Film. The outline of my talk is the introduction, fundamental aspect of silicon, why silicon is not an optical material, and so on. Then I will discuss about the method of synthesis, how silicon nanoclusters can be synthesized. Then what method I have used for the synthesis, that method is called an implantation method, that I will discuss in short. Then experimental details, result discussion, and then conclusion. So let us first of all understand. Nowadays we are using the optical devices, basically the LED, the laser, and all other devices which are there optically available, optical devices. There we are not using silicon as a principal component. What is the reason? The reason is it is a material which has low band gap, that is 1.12 electron volt at room temperature. This band gap is not sufficient for the emission of light radiation. So that inherent mechanism itself is not there with silicon to do this kind of emission. So we can see that there is the indirect band gap nature when we talk about the conduction band and valence band. Then electrons transition with the hole. We don't get. This is about your. This is what about silicon. This is called. One minute, just hide this. Gallium arsenide. We have gallium phosphide. Third and fifth group compound semiconductor materials. They actually have the power of giving large band gap, large we can say energy output, which is in the visible region basically, so that we can have a light output. But then comparatively, the cost is bit more compared to silicon. Obviously, LEDs nowadays is on bulk and largely available, so that is why the cost is effectively not much. Now, what is the solution? So, is there any solution? What can we use? Because silicon is on a major scale, it is available. It is a silica silicate. It is available on large scale everywhere in the world. So, can we utilize those material to develop these optoelectronic devices? The answer is yes. But then there are certain things that we have to understand that how we can do that. So, if you see the nanotechnology and nanomaterials are developing day by day. So, can we synthesize silicon at nanoscale? Then the optical property may change, and that property and that process of the method, which is called the quantum size effect. In bulk semiconductor, we see that the particle dimension is, because if you take a sample of silicon, it is very large, and then electron which is moving inside the material, we say that from the valence band to conduction band and so on. So that mean free path is definitely larger than the de Broglie wavelength. When the size of the nanoparticle become very less, in the size of the sample of the silicon, if you take, it becomes very less. You can see over here, this is the three-dimensional quantum dot. The progression from a bulk towards the one-dimensional material in two-dimensional nanomaterial. These are nanomaterials, and we see this is three-dimensional nanomaterial where we see the energy is getting converted. The band is getting converted in from bulk to, you can say here, it is changing into the discrete one, where so the energy value becomes discrete instead of continuous. This is the process called quantum confinement, where the we can say just a moment. We can say that our electronic motion will be restricted. That is called as confinement, so that it will have a specific energies to access, and then there will be a possibility that when it jumps or it does the transition from conduction band to valence band, then it may emit the light radiation which is in the visible range. This is what the process of quantum confinement, which can be achieved when we synthesize the silicon at nanoscale. That is what we have the aim. Certain papers they have reported also, like you can see there is a synthesis of silicon nanocluster in SiO2, which is some kind of topic I have also taken in the research. So there is a paper in 1998 that he has shown that when we are implanting silicon or mixing silicon nano, we are developing silicon nanocluster in SiO2 thin film. then there is a possibility that you can see before there is a band gap of 1.1 electron volt, and then the band gap changes to, or this is the band gap of a nanocluster just beside to the conduction band and valence band of bulk silicon. So we see that this one has, it is larger comparatively. This side, your photon is emitted. This is the experiment called photoluminescence, in which it is showing that there is the emission of 1.7 electron volt energy photon. So we say that there is a possibility that the light energy can be emitted. There is a method called effective mass approximation. That is the theory which explains how the nanoparticle can produce optical light. There are certain research papers, those who have explained about the porous silicon, doping of silicon with erbium, silicon carbide nanocluster in uh, silicon, beta iron silicide, silicon nanocluster in SiO2, Al2O3. These are the different type of research which is going on actually nowadays on a larger scale. Now, what are the different methods of synthesizing silicon nanocrystals? There are different methods. Basically, most of you must be there in semiconductor research, maybe knowing how the nanoclusters can be developed. Physical method, chemical methods, sputtering, ion implantation, electrodeposition, chemical vapor deposition. But compared to all the method, why we have selected ion implantation? Because it has the advantage of controlling the concentration and depth of the dopant, where we want to actually develop the nanocluster, that I know, controlling the process parameter in the sense of energy, the we can say, and the depth of the this thing can be calculated by methods, electrical and optical selective area, quantum, future quantum computers. It's an application. This is the application that why we want only an implantation to use, because there are certain reasons that quantum computers need a very accurate kind of a development of, the nanomaterials, or the kind of chip technology requires this kind of method to develop. So definitely it is very important method to develop the nanomaterial that we have selected. This machine you can see in on your screen is in IUAC, Inter University Accelerator Center Low Energy Ion Beam Facility, LEIBF, which is in New Delhi, which is I think it was the Nuclear Science Center actually. It was, now it is IUAC, where all these implantation facilities are there. We have used this machine, and it is 2000 kV high voltage machine. Uh, so advantage of negative ion implant. Yeah, in our research, we have not used normal silicon like silicon positive ion or normal silicon ion, which is used generally. We have used silicon negative ion. Then what is the reason behind? Because the negative ion does a very, normal ions if you are using for the implantation, when it is hitting the surface, what happens? It creates some charging effect. And then when you are trying to develop some devices, that charging effect will restrict you, or it will make some kind of disturbance. So the better is that you use negative ion implantation, so that no surface charging effect will not be there. It will be very less. Okay, if it is very large in amount, then it may break down your thin film material. It has a low electron affinity, so it helps in developing the nanomaterials. So that is called atomic bonding process. And then we don't have to use the neutralizer. So extra machinery and the cost all will be not be used. Now, how it happens when a particular ion goes inside the material? What are the actually process? If an ion of energy E enters to the solid target and moves the distance x, then the differential function d by dx is called stopping power. Because anything which you are hitting inside on a surface is not immediately going to go inside. There are certain things which will restrict. Definitely, there are the atoms. In the atom, there are electronic structure. It is going to restrict. So there are two different type of energy losses. One is called nuclear energy loss. Another is called electronic energy loss. These are the stopping mechanism. That ion goes inside. This is called channeling. It depends upon the structure of the the host material, which is called. In our case, it is silicon dioxide. So it is not a crystal material. Definitely, it will not have the channeling effect much. But then we have to calculate how much depth it is there. There is a method called shrink. By using that, we measure how much the ion will be going inside. So that calculation we have done. I cannot show everything over here, but there are methods. So this is the experimental detail that we have selected. Like our sample is called silicon dioxide, 300 nanometer thickness, surface thickness above the substrate, silicon negative ion. 100 kilo electron volt energy is selected for this ion to be implanted with. This is the kinetic energy. Then the projected range was calculated at 170.5. So if you see 300 nanometer and it is going where 170 almost. So it is not very much beneath or not at deep level. It is somewhere just more than middle position. So this is our aim to develop the nanocluster at this particular range. Then these are the ions, number of ions per centimeter square we are going to implant, or we have implanted or made the sample. These are the values of energy losses where it has been calculated. Now our experimental, if you talk about what we have, what are the processes we are checking, what is happening inside the sample, and how we are calculating the amount of silicon negative ion implanted inside to develop the silicon negative silicon nanocluster. So the first and foremost was that we did this SEM can say scanning electron microscopy, where we wanted to find out the surface morphology, but then that was not very useful. But we have taken one very important data, what was called LG dispersive X-ray analysis. In that, what we have seen that when we implant the this is the non-implanted sample, so it is a bare sample of SiO2 of 300 nanometer thickness. So we see that these are the calculations coming out from the EDEX analysis, where we have oxygen at this particular percentage out of 100, we say percentage value in terms of you can say their atomic percent and then weight percent. So oxygen has 29.6, 70%, 70.4 atomic percent. Weight percent is this values, which is total 100. Now, when you implant, we see that oxygen, because when the ion goes inside, it breaks the structure. So SiO2 means there will be some breakage of the SiO2 bond, and silicon will go through, so that there will be additional silicon ions will be accumulating inside. So that silicon will have some increase in the percentage value. So this is, you can see 73.52 over here. Weight percent compared to this is increased. Same in the higher fluence, when you increase the number of ions, we see that there is an increase in the amount by this around 6% increase over there. Then again, weight percent of oxygen is decreasing and weight percent of silicon is increasing. So in this way, we verify that whatever we are doing is actually happening inside. It's not like that we are doing something and then it is because already silicon is there in the silicon dioxide. But what about our silicon which is going? How to measure the values? So this particular analysis gives you the idea that there is clustering or not the clustering, but then accumulation must be going on. Now what to do? How to do the measurement of the nano cluster size, and then whether the band energy is changing or whether what is our aim to get the optical output is happening or not. So what we have to do? So what we did, we have done this particular analysis. Like after the development of the samples, what we did, we had done the measurement of UV, that is called ultraviolet visual NIR, near infrared analysis. So what we have measured is the transmission against the wavelength. So when the sample is kept in the transmission mode, what we have seen that non-implanted sample we have, because the title of the talk is annealing effect. So when we done the implantation, we have collected three samples over here. One is the sample of silicon negative ion 116, one into 10 to 16, 5 into 10 to 16, and 1 into 10 to 17. So we say it is increasing by the factor of 5 and then over here. Okay. So we say that three samples which are there unannealed and then three samples annealed. What is the difference we see? The difference is that transmittance of annealed samples are higher than the unannealed samples. This indicated the presence of new SiOX phase. I am not saying it is nanocluster, but it will be a phase which will be developed because of silicon going inside and developing some new structure which will change the transparency, or which will change the transmission ability of the material inside. And that is what happening because of the you can say clustering effect. Then we see that energy band gap calculation, we have done the measurement of all the samples we have done. Then we can see there is a slight change from the unannealed to annealed samples. So the slight change is around, you can say not very much, but then somehow it is changing. And if we develop if you go on improving the sample quality and the number of ions and the temperature, then definitely there are evidences that we get better and better band gap result, which will be going towards because photoluminescence experiment we have done that I have not included because that is already published. So in that we have obtained that the band gap has changed drastically, and we have not concluded, but we have said that we have reached to the result that there is an optical property possible when you grow the silicon nanocluster at certain dimension. Then we can say this is very important analysis, glancing angle X-ray diffraction. So we have taken this particular analysis to find out whether at a particular, because this was not done at the same temperature, it was done at 500 degrees Celsius. The glancing angle was 2 degree because it is a glancing angle, so it is not very much going inside, but it is a analysis which will reach toward the where the actually sample your nanocluster has been developed. So 116, 516, these are the two samples we have taken. One is the non-implanted sample, which is the this one particular peak which is there. So we see that when the non-implanted and as implanted samples A, B, and C, we say over here these are the three samples. After annealing, we say that the peak has been decreased. It means when we are talking about the annealing process, again there is a change in the phase. There you can see there is a shift in the P position also. So there may be some kind of a, stress has been developed inside because of interplanar spacing, inclusion of new particular ions inside. The development of clustering has happened. This is what we reveal from this particular data or your graph, and then we have calculated by using the crystallized size.
So, sir, time is over.
Yes, ma'am. This is the almost the last slide. Yeah, crystallized
Yeah.
size we can say when we are measured the two samples, we have done the analysis for two samples, that is 116 and 516. When it was calculated, these are the samples. The calculation it was done before annealing. There was no thermal treatment given. But the moment we gave the thermal treatment, actually, unfortunately, we could not do this well cancer analysis for this angle. But 2 degree we did properly. So we got that there is an increase. It means after thermal annealing, there is a coagulation and agglomeration may happen, and there a clustering of nanomaterial, nanosilicon can take place. So 15.14 and around 13 or 15, we get the values measured, and then we definitely say that the uh, nanocluster is possibly is getting developed inside the sample of SiO2. So that we have done at around 500 degrees Celsius, 45 minutes, and then this was the calculated. Now, in conclusion, what we reveal, the EDEX studies reveal that an increase in the weight percentage, atomic percentage, that there is a presence of silicon cluster inside of increasing fluxes with respect to increasing fluxes. Implanted samples were thermally annealed at the temperature of 900 degrees Celsius under nitrogen ambient. Then the UV visual studies showed higher transmittance for thermally annealed samples as compared to unannealed samples. This may be attributed to the creation of again a new SiOX phase inside. This study also revealed that there is we can say, it is correlated with it that there is the presence of nanostructure of silicon. And again, GXRD anything process promotes nucleation of SiOX phase. So the aim of our particular uh, experiment and the research is to develop silicon nanocluster for the optical device formation, and which is a progress towards achieving that particular aim. So these are the references that I have taken. These are few references. Thank you very much for your kind attention, everyone.
Today, my presentation topic is investigation of ultrasensitive wave theory-based analytical approach using BGB. Those all are co-authors of this paper. At first, abstract. Actually, in this paper, in this present study, it is present a analytical study of a wave theory-based fiber optic biosensor using Bessel-Gauss beam for the detection of bilirubin. For that purpose, we have used multimode fiber whose core diameter is 100 micrometer. After removing this cladding, we have used bilirubin as a sensing layer whose thickness is 90 micrometer. By using this approach, we obtain sensitivity is 10.16 times better than the proposed sensor where Gaussian beam is used as a source. These all are my contents which I have used. And now, at first, a study related to bilirubin. Actually, bilirubin is a metabolic product that generally secreted through bile and urine. Elevated level of bilirubin leads to jaundice, which is nothing but a yellow discoloration of eyes and skin. In case of severe jaundice, bilirubin can accumulate in brain, which results in irreversible brain damage. For neonates liver, that means for newborn babies, there is not sufficient enzymes and present. In that case, typically increasing temporarily bilirubin in their body. So this level of bilirubin it is required to monitor. So the level of bilirubin for human in normal case it is 20 micromole per liter. For jaundice case, it will be greater than 50 micromole per liter. For neonates babies, this in case of jaundice, its level is 0.05 gram per liter. Now, the most effective conventional method to diagnose the bilirubin is phototherapy. In that case, the medical range. But in this conventional method, blood time to time in order to determine the required dose and future course of action. So now the disadvantage of this conventional method can be overcome by using fiber optic sensor. Now the advantage of this fiber optic sensor for the detection of the bilirubin are it is rapid and level phenomena. That means it don't require any radioactive component which is required in the conventional method. It is highly sensitive chemical inertness. It is in situ real time and remote sensing. It is immune to electromagnetic interference. It is high response time. As a result, it is minimal in size and simple in use. Now, existing fiber optic sensor for the detection of bilirubin are U-bend structure, D-shaped structure, fiber break grading, long period grading, tilted fiber break grading, SMS structure, bending, and so on. But all this method having some limitations, like there is a limited overlap between the guided mode and the cladding material to be detected. As a result, there is a limitation for there is a limited sensitivity. At the same time, there is some limitations like fabrication complexity and mechanical insecurity, which creates a challenge towards the sensor design process. And so all those limitations can be overcome by using non-Gaussian beam instead of using Gaussian beam as a source. It is also expected that if we use non-Gaussian beam like zero-order Bessel-Gauss beam as a source, this sensitivity is further be increased. Now, what is Gaussian beam and what is Bessel-Gauss beam? Actually, Gaussian beam is an electromagnetic radiation whose transverse magnetic and electric field amplitude profile are given by Gaussian function. And Bessel beam is a field of electromagnetic wave whose intensity distribution is described by the Bessel function. This is the intensity profile of Gaussian beam. This is the intensity profile of Bessel beam. Actually, practical Bessel beam is called as Bessel beam, and what is theoretically presented beam, it is called as Bessel beam, and practically what we obtained, we call it as Bessel-Gauss beam, but its profile is similar. So in case of Gaussian beam, maximum intensity is present at the center and the clad interface, there is no annular rings. But in case of Bessel beam, multiple annular rings are present at the clad interface. As a result, there will be more absorption at the clad interface. So there is possibility to obtain more sensitivity as compared to this Gaussian beam. Now here in this study we have used wave theory instead of using ray theory. Now advantage of wave theory over this ray theory are actually to analyze the higher order mode within the fiber, wave theory is more convenient and effective rather than ray theory. And the similarity between analytical solution and experimental solution can also be achieved by using this wave theory based approach. Also more accurate analysis of the self-image effect within the multimode fiber can also be materialized by using this approach. Now proceed to my schematic diagram. Here at first, polarization maintaining fiber coupled broadband laser source is used as a source which is collimated by using lens L1 and L2. After that, it is propagated through this hexagon whose apex angle is 140 degree. Then, and the other end of this hexagon, zeroth order Bessel Gauss beam is generated. After that, it is propagated through my sensing scheme. Here, two H1 fiber, that means two higher order mode fiber is coupled between this multimode fiber. Here, after removing this multimode fiber, here we have used this bilirubin, which is used as a sensing layer. Now with the change in wavelength of this source, the refractive index of this bilirubin and this refractive index of this core is changes. As a result, transmitted power which is observed by this optical power meter head is changes. By observing this, we can easily detect the early stage of the bilirubin. This all actually this proposed scheme is we have done by using this analytical simulation. For that purpose, we required some equations. So these all are my related equations. So power coupling coefficient for each radial mode is obtained by this equation. When the input is Gaussian beam, in that case input field is obtained by using this equation. When the input is zeroth order Bessel Gauss beam, in that case input field is obtained by using this equation. Now the distribution of the electric field for the breath guided radial mode inside the fiber is obtained by using this equation. Here, this J0 and J1 term represent the Bessel function of first kind of order 0 and 1 respectively, and K0 and K1 is represent the modified Bessel function of second kind of order 0 and 1 respectively. Now, I0 is represent the modified Bessel function of first kind of order 0. Now the coupling coefficient for the second order for the second layer, when the input is Gaussian beam, is obtained by using this equation. Where the coupling coefficient for the Bessel Gauss beam for the two layer structure is obtained by using this equation. Now transmission loss is obtained by using this equation. Now proceed to figure 1A and B represent the power coupling coefficient with respect to radial mode number. Now first figure represent for Gaussian beam and second figure is represent for Bessel Gauss beam. Here in that case, the maximum mode dominating number is for Gaussian beam, it is 11. Sorry. Hello. Hello.
Yes, you're audible. You're audible, Vijaya. Yes, you're audible. You can continue.
Okay. Here maximum mode dominating number for Gaussian beam is 11 and for the Bessel Gauss beam it is 40. So higher order modes are activated in case of Bessel Gauss beam. As a result, higher order modes are activated. So in that case, here we will get the higher sensitivity as compared to this Gaussian beam. Also in case of Gaussian beam, the 5.7% of the input power is coupled in the maximum mode dominating number. But here in this case of a Bessel Gauss beam, here 12.4% of the input power is coupled in case of Bessel Gauss beam. Now proceed to figure 2A and B represent the transmission load with respect to propagation length. When this is for Gaussian beam and this is for Bessel Gauss beam, and this is obtained when the input is 450 nanometer and here the concentration of bilirubin is 0.05 gram per milliliter. Here from this figure we can see, here in case of Gaussian beam, here we are getting less loss as compared to this Bessel Gauss beam. Here we are getting more loss, that means as there is more higher order modes are activated in case of Bessel Gauss beam, so here we are getting more loss as compared to this Gaussian beam. Proceed to figure 3 and B represent the transmission loss with respect to wavelength. When this wavelength is changes from 430 to 630 nanometer and the concentration of bilirubin is fixed at 0.05 gram per liter. Here, in case of Gaussian beam, the transmission losses varies from minus 6.57 dB to minus 12.84 dB. But in case of Bessel Gauss beam, it is varies from minus 35.14 to minus 47.92 dB. So here we are getting more loss as compared to this Gaussian beam. Now, the table 1 represents the comparative analysis of the sensitivity. Here, in case of here, after comparing this table, we can see by using this Gaussian beam and using my proposed scheme. Here, when we are comparing, so in case of Bessel Gauss beam, here we are getting more sensitivity as compared to this Gaussian beam. Now, proceed to my conclusion. Actually, here we have used wave theory and Bessel Gauss beam as a source, and we have used multimode fiber whose core diameter is 100 micrometer, and the sensing layer is 1 millimeter. After removing this cladding, we have used bilirubin as a sensing layer. So by using this proposed scheme and using Bessel Gauss beam as a source, here we are getting more sensitivity, which is 10.16 times better than the proposed scheme using Gaussian beam as a source. The proposed biosensor also intend to improve in existing fiber optic sensor in terms of sensitivity and resolution for the detection of bilirubin. So the proposed idea will produce a better sensing platform to identify hyperbilirubinemia through the optical assessment of the earlier stage of hyperbilirubinemia. These are all my references. Thank you.
Myself, Dr. Somanathan, working as a professor in the Department of Chemistry, School of Basic Science, and Wells Institute of Science and Technology and Advanced Studies, Chennai, Tamil Nadu, India. First of all, I take the opportunity to, thanks to the organizer to give me the opportunity to present my work. My topic is how to control the diameter and wall thickness of the carbon nanotube. You know that already previous speakers talked about many carbon-based material like a carbon nanoparticle as well as a graphene and carbon nanotube. So due to its unique properties, due to that one, it has been applied in many fields like transistors, chemicals, or biosensor, even electrical, mechanical, and thermal properties are there. So for that, we need to have a proper diameter of a carbon nanotube and wall thickness can be controlled. How to control the diameter and wall thickness of a carbon nanotube? By processing the parameter like a catalyst size and composition, carbon feedback, temperature and gas flow, like a chemical vapor deposition parameters, other parameters. For wall thickness control, you need to have a catalyst size and the growth condition need to be followed, and the gas flow and the pressure need to be followed, and the types of carbon sources and catalyst type need to be understood. After both these things, we need to analyze whether what type of carbon nanotube can be obtained, whether a single walled or multi-walled or a double walled carbon nanotube, using a technique such as a TEM transition electron microscope or even a Raman spectrum. We can identify whether the single walled or multi-walled can be identified. So in my studies, I have done the CNT obtained by our process. We are using a aluminum support as a layer, and we are doping a 1 nanometer thickness of a iron nanoparticle on the aluminum supported layer using a technique called as the IBS, iron beam spectrum technique. And I use that material for the synthesis of single wall carbon nanotube at a temperature of 700 degrees centigrade. So in that material, when we are using a 1 nanometer iron thickness catalyst particle, I'm getting both a single walled carbon nanotube as well as a double walled carbon nanotube. When I go with the same catalytic process at a low temperature, there I'm switching over to double walled carbon nanotube as well as a multi walled carbon nanotube. So this is the how to vary. Here in this figure, we can clearly establish how the temperature is varies. So the single walled carbon nanotube as well as double walled carbon nanotube at low temperature, what will happen? Whether a multi-walled or double walled, the wall thickness is increasing. When you increase the thickness of a catalyst, 0.5 nanometer, 1 nanometer, or beyond that 1.5 nanometer, so when you increase the thickness, the tube diameter also increases. You can clearly see here. So at a temperature of 700 degree with iron catalyst 0.5 nanometer or 1 nanometer with a supporting layer of 10 nanometer of aluminum, so we can get both a single walled as well as a double walled carbon nanotube. So in this condition, you can see the 0.1 to 1 nanometer thickness of a catalyst, we are getting only a single wall or double walled carbon nanotube. Whereas beyond 1 nanometer thickness of a catalyst, we are getting a double walled and multi-walled carbon nanotube. So this is identified process. Similarly, when you go for a carpet or a forest or a growth of vertical aligned carbon nanotube, same physical condition, chemical physical condition have been seen. When you have a smaller active particle, the temperature and the pressure is limited. So increase the size of the particles, the thinner the catalyst, like a 1 nanometer or 0.5 nanometer, or even I decrease the thickness of the catalyst, 0.37 nanometer. Later process called here we clearly see 1 nanometer, mostly double and single nanometer beyond 2 nanometer diameter of the carbon. Whereas in the case of here 0.5 also we are getting less than 2 nanometer. Then here at the point here clearly we have given with pressure what will happen when you increase the amount of the pressure in the catalyst, you are taking 0.5 nanometer. The nanometer 0.3 there is a point T about 2 nanometer, and when we increase the temperature pressure at 5, getting 3 to 4 nanometer. So this is the process we identify. So what is the main thing now? The catalyst can be obtained either by chemical method or nanoparticle in a solution, or physical methods such as a plasma or a spartan deposition, thermal treatment of thin film catalyst for the. So the size catalyst used in the growth process directly affect the diameter of the carbon nanotube. Increase the large the thickness while small nanoparticle with the inner cylinder. So this is our control. We can see in the graph. We can check what's when you thickness of the catalyst. So here we have left in the at least 1 to 0.5 nanometer thickness of the catalyst is very good for to obtain a stable wall carbon. This is our conclusion. Thank you.
Good afternoon, everyone. Myself, Manojna R, and today I will be presenting my topic, which is entitled as Dexterous Green Synthesis of Cu2O Nanoparticles, an amenable catalyst for aqueous click reaction, antiproliferative and wound healing applications. And this work is carried out under the guidance of Professor Ravindra R. Kamble. As we know in recent decades, how nanotechnology has taken over the world, not only in medicinal and research field, but also in science and technology. And as we know, copper is one of the most widely used material in the world. Considering that copper oxide nanoparticles particularly have piqued the curiosity of many researchers because of their broad array of applications. And the current study demonstrates the ecologically benign synthesis of novel copper oxide nanoparticles. As we know, like how in our daily schedule, we use sugar mainly in our diet, and it is also very considered as a poisonous thing to do in our daily diet. So thinking of that, like when I thought about the coastal area, there they use mainly solid jaggery as the sweetener. And so that thought came to us, why not to use solid jaggery as the reducing agent? And here, therefore, in this endeavor, we use solid jaggery was used as reducing and capping agent to synthesize our nanoparticles. And it is the most prevalent kind of solid. And it is also brimming with carbohydrates, iron, protein, vitamins, and most notably vitamin C. And this is our scheme 1, in which we have synthesized our copper nanoparticles using copper sulfate as our precursor and using solid jaggery as the reducing agent. And then we used NaOH to maintain the pH, and it was kept in oven to dry, and later it was used for further studies. As we know, it is also used, copper nanoparticles can be used as catalyst and in anti-cancer, wound healing, as well as in drug delivery studies. So the synthesized copper oxide nanoparticles were further characterized using XRD, SEM, FESEM, EDX, UV visible. Particle size was also used to characterize the nanoparticle size, and also we did FTIR for both solid jaggery and as well as copper oxide nanoparticles. In XRD, we could see the crystallinity and also the Bragg's diffraction angle we calculated, and we could see the Miller indices at 5 major peaks, and it also well agreed with the dB card number. And in FESM, we could see the spherical shape of the nanoparticles, and in EDX, we could see the core elements, which are copper and oxygen. And in UV, we got the 684 nanometer as the lambda max. And from DLS, we calculated particle size around 57 nanometer. We also calculated zeta potential stability around plus 65 millivolt. Then further, we utilized the copper oxide nanoparticles as nanocatalyst in the infamous click reaction, which also got its Nobel Prize in 2022. So here we used solid Jaggery synthesized copper oxide nanoparticles as an efficient catalyst to synthesize 1,4 substituted 1,2,3 triazoles in water. And here we used substituted aniline, and it was diazotized using sodium azide. And we synthesized 2A2G, that is substituted aryl azides. Then subsequently, we took phenyl acetylens 3H2I, and then they were reacted with the azides to give the yield 4J2W, which are 1 to 3 triazoles. The synthesized compounds were further characterized using IR, proton NMR, C13, and mass. Here, in proton NMR, we could see the proton of the triazole ring, which we got around 8.19 ppm, and in also C13, we could see the peak of carbon of triazole ring, which is around 148.52 ppm, and the carbon attached to nitrogen in the phenyl ring was observed around 137.15 ppm, and the molecular weight was confirmed by using mass spectrometry, and it was molecular ion peak was observed around 222. Then we explored it further for anti-cancer activity, and we know cancer has increased mortality and morbidity worldwide, and in particular, breast cancer and cervical cancer has prevailed more among women. And we thought to explore it further for MCF7, MDMB231, and HeLa cell lines. And the conventional MTT technique has been employed in this work. And the green synthesized copper oxide nanoparticles were tested against the breast cancer cell lines and cervical cancer cell line. And the copper oxide nanoparticles have shown substantial efficacy in all examined cancer cell lines by suppressing more than 70% of cells. And even the IC50 of Cu2O nanoparticles were recorded as 51.24, 59.24, and 64.80 for HeLa, MCF7, and MDA-MB231 cells respectively. When we see the morphological image of the microscopic data, here we can see as we increase the concentration of the drug copper oxide nanoparticles, we can see decrease in cell viability, and also the cell shrinkage, cell turgidity, and cell blabbing could be seen in all 3 major cancer cell lines. Next, we increased our further work to wound healing activity as well. And the current study used an in vitro scratch assay test to examine the wound healing capabilities of copper oxide nanoparticles. And for this experiment, normal L929 fibroblast cell line was used. And here we could see that the untreated cell didn't show much cell migration as compared to standard ascorbic acid and copper oxide nanoparticles. With time, we could also see increase in the percentage of closure of wound, and it was observed around 24 hours that it was almost closed in both ascorbic acid and copper oxide nanoparticles. So concluding with this, we have developed a facile innovative method utilizing solid Jaggery, which provides a simple and efficient route for the rapid green synthesis of Cu2O nanoparticles. This is a significant advancement, being able to synthesize Cu2O nanoparticles very rapidly compared to our previous reports. Consider the scope and surge in nanoparticle biosynthesis research in recent years. This sector looks to be on the cusp of significantly more broad and extensive application research, and also the regioselective union of terminal alkynes and organic azides, which is copper 1 nanocatalyzed click reaction, results in 1,4 di-substituted 1,2,3 triazole, and it also demonstrates an incredibly broad range of exquisite selectivity. And the Bio-Cu2O nanoparticles which were synthesized also displayed in vitro anti-cancer activity against MCF7, MDA-MB231, and HeLa cell lines. And our results further suggest that also Cu2O nanoparticles have an excellent wound healing property, skin regeneration, which has in the wound healing. Thank you.
So this is SIVASANKAR from Annamalai University. I am doing the PhD there, and my topic is biosynthesis and photocatalytic application of carbon dot selective coinage metal oxides. So here we are taking copper oxide and a silver oxide nanoparticle, and we are preparing that through co-precipitation method, and we are trying to dope with the carbon 12 on one side and the graphite powder in another side. So with the bare, what's the role on the blue dyes that we are going to do actually. This is halfway down. It's not completely over. Kindly excuse that, because we have done the precipitation method. I mean, the NEPs are ready and doping is done, but we need to carry on the photocatalysis process. And the preparation of CuO is done by biological method, and we have taken that henna extract, which is heated to about 70 to 80 degrees Celsius for about 20 minutes, and the extract is treated with 0.3 molar copper chloride solution with a constant stirring, and that is given calcination for 350 degrees Celsius for 5 hours, and we got a copper oxide nanoparticles. This is one side, and the same way we proceeded with the henna extract with the solution mixing with copper nitrate, silver nitrate solution to get the silver nitrate thing. So the same, the methodology is formed to, used to prepare silver oxide nanoparticle as well. And doping is carried out with henna extract. Doping is carried out with henna extract, and separately we are doing doping with the chalk graphic powder as well. And now we got the samples, the FT-IR and the XRD samples, and these are the FT and IR, AGO nanoparticle samples and the CuO nanoparticles samples and henna powder. And we are in still discussion with the peaks ranges here. And this is with the, we have done the silver oxide nanoparticle with 0.15. That is, if you take, 3 molar of the sample, that is silver nitrate sample, we will use to take, half the molar of it. That is, 1.5 molar of it and a charcoal. And these are the FTR reports. And we are looking on action on dyes. Mostly we are going to do on blue dyes. And since NI is itself a dye, we are trying to look on that as well. Yes, sir.